In this session, we will discuss about Laplace transforms. Laplace transform has so many applications. One of the most important application of Laplace transform is we can easily find out the solution of linear ordinary differential equations using Laplace transform. So, let us start our module for Laplace transform. First, we have to see integral transform. If f of t is a function of t defined for t greater than or equal to 0, then its integral transform is defined by capital F of s is equal to integral 0 to infinity k of st f of t dt, where k of st is called the kernel function. That means the integral transform transforms function of a variable t to a function of a variable s. Using this integral transformation, we can easily solve complex problems. Okay, that is the application of integral transforms. Then next is Laplace transform. Laplace transform is an integral transform with a kernel k of st is equal to e raised to minus st. That means we can define Laplace transform as if f of t is a function defined for all t greater than or equal to 0, then the Laplace transform of f of t is a function of s and it is denoted by capital F of s. Since f of s is a Laplace transform of f, it is also denoted by capital L of f and it is defined by capital L of f, that is Laplace transform of f of t. Similarly, we can write it as capital L of small f. L of f is equal to, it is an integral transform, therefore it is capital F of s, that is equal to integral 0 to infinity e raised to minus st f of t dt. That means if f of t is a function of t, its Laplace transform, that is L of f, is a function of s. That's why we write it as that L of f is equal to f of s. Laplace transform of f is a function of s. Capital F of s, that is equal to integral 0 to infinity e raised to minus st f of t dt. Using this transformation, we can transform f of t to a function of s. So, next is some problems. First question is find f of s. That means we have to find out the Laplace transform. Find f of s for f of t equal to 1 where t greater than or equal to 0. That means we have to find out the Laplace transform of f of t, that is Laplace transform of 1. So, f of s is equal to L of f, Laplace transform of f is equal to, here f is 1, therefore that is equal to L of 1, that is equal to, what is the Laplace transform of f of t? It is integral 0 to infinity e raised to minus st f of t dt. Therefore, that is equal, L of 1 is equal to integral 0 to infinity e raised to minus st. Here f of t is 1, therefore it is into 1 dt. That is next. What is the integral of e raised to minus st? With respect to t, it is e raised to minus st divided by the derivative of minus st with respect to t, that is minus s. Limits are 0 to infinity. So, applying the limits 1 by minus s. S is constant with respect to t. Therefore, minus 1 by s taken outside into applying the upper limit, it becomes e raised to minus infinity minus applying the lower limit, it becomes e raised to 0. E raised to minus infinity is 0, therefore it becomes minus 1 by s into 0 minus 1, that is equal to 1 by s. So, what is the Laplace transform of 1? It is 1 by s. Next question is find the Laplace transform of f of t equal to e raised to at, exponential function. L of Laplace transform of f of t is L of e raised to at. L of e raised to at is equal to integral. What is the general formula? Integral 0 to infinity. L of f is integral 0 to infinity e raised to minus st f of t dt. That is, therefore, L of e raised to at is equal to integral 0 to infinity e raised to minus st into, here f of t is e raised to at. E raised to minus st into e raised to at into dt. Then combine the exponential terms, that is e raised to minus of s minus a t. Expanding we get e raised to minus st, e raised to plus at. So it becomes e raised to minus of s minus at dt. Integrating with respect to t, it is becomes e raised to minus of s minus at divided by derivative of a minus of s minus a into t is minus of s minus a, varying from 0 to infinity. Then minus of 1 by s minus a is independent of t, therefore we can take it outside. Minus of 1 by s minus a into, applying the limits, e raised to minus infinity minus e raised to 0, e raised to minus infinity is 0, therefore it becomes minus of 1 by s minus a, 0 minus 1, therefore it is 1 by s minus a. So the Laplace transform of e raised to at is 1 by s minus a. Next question is, next is how to go through the linearity property of Laplace transform. Laplace transform is a linear operation. That means if we have that means L of a into f of t plus b into g of t, where a and b are constants, f of t is a function of t, g of t is a function of t. Then L of a into f of t plus b into g of t, that is equal to a into L of f of t plus b into L of g of t. Next question is, find the Laplace transform of sin h at, hyperbolic function. Laplace transform of sin h at is denoted by L of sin h at. L of sin h at is equal to, we can use the relation, we can express this hyperbolic function in terms of exponential functions. That is, sin h at is e raised to at minus e raised to minus at divided by 2. Applying the linearity property, that is 1 by 2 into L of e raised to at minus 1 by 2 into L of e raised to minus at. Then we know that the Laplace transform of L of e raised to at is 1 by s minus a. And if a is replaced by minus a, then instead of a it is minus a. So L of e raised to minus at is 1 by s minus minus a, that is s plus a. So L of e raised to at is 1 by s minus a, L of e raised to minus at is 1 by a is replaced by minus a, that is s minus minus a, that is 1 by s plus a. Applying this here, and then we can find out the LCM as s minus a into s plus a, that is s minus a into s plus a is s square minus a square. That means numerator become s plus a minus of s minus a. Simplifying we get a by s square minus s square. So the Laplace transform of sin h at is a by s square minus s square.